Thanks all the organizers, and happy birthday to Professor Mark Lewis. I'm Xiunan Wang. I'm assistant professor from the University of Tennessee at Chattanooga. Today, I'm going to introduce how to use θ-Diffusion equation to investigate rabies transmission in spatially heterogeneous environment. And this is a joint work with Professor Wang and Professor Michael Li. Okay, so first, let's look at why do we care so deeply about rabies transmission. This is because rabies is really a horrible disease. It's caused by the rabies virus, and this virus exclusively attacks the central nervous system. And once the virus arrives at the central nervous system, the disease is invariably fatal. No cure can save the lives. And in addition, as human population keeps increasing and expanding to new geographical areas, more people live in close contact with animals, and such a close contact with animals will increase the possibility for the disease to pass between animals and people. So it's urgent to control rabies transmission. Although all mammals can transmit rabies, dogs account about 99% of all human rabies deaths globally. And the vaccinating dogs is the most cost-effective control measures. So in this work, we will focus on rabies transmission in dog population. Then why do we need to consider spatial heterogeneity? Well, this is because spatial heterogeneity really matters in rabies transmission because rabies are usually transmitted over a large geographical region. For example, large rivers and high elevation peaks in mountains are both being found to dramatically affect rabies transmission. And the spatially heterogeneous environment we will consider in this study is the citywide scenario, because this is closely related to human public health. So we are mainly curious to know how is rabies transmitted among dogs between a city region and a wild region. And how does the control measure in a city region, for example, vaccination in the city region can affect the transmission of rabies in a neighboring wild region, and vice versa. Note that the vaccination strategies in the city region and in wild region are quite different. In the city region, the dogs can get vaccinated in animal hospitals, but in wild region, vaccinations are distributed by helicopters. And to develop a spatially heterogeneous rabies model, we think about using θ-Diffusion equation. θ-Diffusion equation can be derived from a random walk model. Potter, Spelager, and Mark Lewis derived such a θ-Diffusion equation. And here in this equation, U of xt can be regarded as the population density at location x and at time t. And d of x is the diffusion rate. So a special case is when theta equal theta is a parameter that reflects the individual dogs make movement decisions. If theta equals 0, then the decision is made at the starting point. And if theta equals 1, then the decision is made at the destination point. If theta is a parameter between 0 and 1, then the movement decision is made based on some intermediate point. So a special case is when the diffusion rate is a constant. Then in that case, the θ-Diffusion equation will be reduced to this simple case. So this is the commonly used model by many authors when they use PV model to describe a population movement. And a more general case is when the diffusion rate d of x depends on spatial location x. Then in that case, the derived θ-Diffusion equation is a family of infinitely many partial differential equations. Because given a value of theta, we'll get a corresponding PDE. And in all the partial differential equations, we have these three special cases. First, when theta equals 0, then the θ-Diffusion equation is reduced to this Fokker-Planck diffusion equation. And it is applicable to describing random diffusion. That is when the probability moving to the left and to the right are equal. The second case is when theta equals 0.5, then we have this Ficken diffusion equation. And in this case, we have the it can be used to describe symmetric movement. That is when the probability of moving between 2 points are the same. And the last case is when theta equals 1, and in that case, we have this attractive dispersal equation. It can describe the case where the transition probability depends on the state at the destination point. So from this table, we can see that if we want to describe random diffusion, then it's more appropriate to use the Fokker-Planck diffusion. Okay, so here is our model. In our model, we only consider the dog population. We do not consider human population. And we partition the dog population into 4 compartments, S, E, I, R, and they represent susceptible, exposed, infectious, and vaccinated compartments, respectively. Note that the diffusion, the movement of infectious dogs and the non-infectious dogs are essentially different. So infectious dogs can only move randomly due to their destroyed central nervous system. So we can assume infectious dogs cannot make movement decisions, and they just wander around randomly. In contrast, non-infectious dogs can make any movement decisions based on the conditions at specific locations. So we can use a Fokker-Planck diffusion term to describe the movement of infectious dogs. And we can use a general θ-Diffusion term to describe the movement of non-infectious dogs. And also we know that the diffusion rate of infectious dogs is much higher than that of non-infectious dogs. So we can neglect the diffusion of non-infectious dogs. So in our simulation, we only consider the model with this single diffusion term. And the other terms are not difficult to understand. A is the recruitment rate. And lambda R gives the rate of immunity, loss of immunity, because the vaccination cannot protect lifelong protection. And beta SI, this term gives the new infections. And 1/sigma will give the duration of the incubation period. And we assume a proportion gamma of the beaten animals will become infectious. And the rest of proportion 1 minus gamma will not develop clinical outcomes. M is the natural death rate. So in each equation, we have this term. And mu is the disease-induced disease-induced death rate. K is the vaccination rate. So both susceptible and exposed population can get vaccinated. And for the numerical simulation, we consider one-dimensional spatial domain with homogeneous boundary, Newman boundary condition. So the spatial heterogeneity is totally reflected in this diffusion rate of infectious dogs. And for the citywide scenario, we can use such a function to approximate the citywide diffusion rate, because in the city region there are a lot of traffics and buildings. So, but in the wild region, the wild region is relatively large and open areas. So the diffusion rate of wild dogs should be much higher than that of city dogs. And we assume the diffusion rate of city dog is about 500 meters per year, and the diffusion rate of wild dogs is about 7 kilometers per year. Next, we substitute this diffusion rate into the model, and then we obtain some simulation result. So next, I will show some selected simulation results. This first one, here we assume homogeneous initial condition. That is, we assume that the initial infections are equally distributed throughout the entire spatial domain. And in this case, we can observe there is an outbreak of the disease with a high peak value labeled in yellow here, and then followed by some outbreaks with smaller peaks in subsequent years. We can also observe an active interface between the city and wild region. So we can, in the right figure here shows the population of infectious dogs at the end of every 10 years. And we can see a peak on the city side near the interface and a valley on the wild side near the interface. So this may be because the diffusion rate of wild dogs are much higher. So there should be more chance, the chances for wild dogs to run into the city region is much higher. And once they run into the city region, their diffusion will be hindered. So they will slow down their diffusion rate, and then it's easy for them to accumulate on the city side near the interface. And next, we also tried different initial conditions. In figure A here, we assume the initial infections are located in the inner city region on the interval from 0 to 25. And in figure B, we assume the initial infections are located in inner wild region on the interval from 75 to 100. And in figure C, we assume the initial infections are concentrated on the interval from 40 to 60. That's between the city and wild regions. And the figures in the second row here are the corresponding observed epizootic weights for each case. So for all these three cases, we can see that the disease spreads to the disease-free area. And we can always observe an outbreak with high peak value and then followed by some outbreaks with smaller peaks. And meanwhile, we can observe that the disease spreads faster in wild region. Okay, so at last we consider the vaccination strategy. So first, we try the city-focused vaccination. If we only vaccinate dogs in city region, then we can see that if we increase the vaccination rate in the city region, then the steady state of infectious dogs in the city region will be decreased. But there is no effect on the infectious status in the wild region. And similarly, if we try wild focus vaccination, that is only vaccinate dogs in the wild region, then when we increase the vaccination rate in wild region, then the steady state of infectious dogs in the wild region will be decreased. So the disease in the wild region can be well controlled. But the infections in city region still remains high. So it's not enough to eliminate rabies in the entire spatial domain if we only vaccinate dogs in the city region or in the or only in the wild region. Okay, to summarize, first, our model is the first one that applies this Fokker-Planck diffusion term to describe the diffusion of infectious dogs. And probably our work is also the first one that use this Fokker city diffusion to investigate infectious disease transmission dynamics. And second, we observed epizootic waves and an active interface between city and wild regions. And the last point is, in order to eliminate rabies in the entire spatial domain, then we need to vaccinate dogs in both the city region and the wild region. Okay, thank you for your time and attention. And once again, happy birthday to Professor Mark Lewis. And here's my interaction with Mark. From February to July last year, before I started my tenure track position here, I was a postdoc co-supervised by Professor Mark Lewis and Professor Wang. I really appreciate their guidance and help. And during those 6 months, we completed the 2 papers about COVID-19 dynamics using differential equations and machine learning. And currently, we also have an ongoing project about memory and learning in animal movement models. And this photo was taken during our MassBio canoe trip in Edmonton. And Mark is very experienced at canoeing. Almost nobody can catch up with him in the river. That's all for my presentation. Thank you.